of the design of power transmission system, and in this system we focus on a speed reducer as we've done in the past lecture. So we're following the same example in which we selected the sizes for the 4 different gears in that system, and we would just proceed with that design. So let's see what we have so far. What we have is the gearbox that we have designed. Has a height or dimensions on the order of 11 or 12 inches, let's say 12 inches. And from that we are able to fit in 4 gears, and when we fit them in we are able to compute the required pitch so that we can fit in the 4 gears. The idea is that we can fit in this Y. We have to fit in the gear D3, assuming that this is the entire diameter. Maybe it's going to go down to here all the way to here. D3 plus half of D2 plus half of D5, and D5 now is going to go up to here. Then we have to add 1 diametral pitch up here and then 1 down here, so it'll be 2 over P. And then we add clearances and wall thicknesses. Writing the relationship between the number of teeth and the diameter via the unknown pitch, we can resolve this equation for the unknown pitch P, given that we know all of the number of teeth that are required. So if you look here, you see that P minimum, you add up all of the teeth that you have to fit in plus 2 teeth, 1 top, 1 bottom, and you divide them by the available distance, basically Y minus the clearances and the wall thicknesses. So the distance Y is 22 inches basically, and we allow 1.5 inch for clearances, wall thicknesses, so we come up with 5.76 teeth per inch. That is the basic pitch that we have. So we're going to go up to round it up to the next integer, 6 teeth per inch, and that will give us a solution for the diameters, because the diameter for the input shaft D2 is the number of teeth that we have, 16, divided by the pitch, so it gives us a diameter of 2.67. Similarly, we can figure out the diameters of shaft 3 and shaft 5, gear 3 and gear 5, then that will be 12 inch. So we have 2 gears at very small, 2.67 inch, and 2 gears very large at 12 inches in diameter. The speeds, we have computed those before. Input is 1750, output is 86.4, and the counter shaft or intermediate shaft has a speed of 389 RPM. We figure the speeds, then we can find the pitch line velocities from gear 2 on gear 3. The pi d times RPM over 12 gives 1223 foot per minute. Gear 4 on 5 gives us 271.5 foot per minute. And from the pitch line velocities, the force will be inversely proportional to these pitch line velocities. The faster it is, the less force it will have. So gear 2 on 3 exerts a force of 540 pounds, but 4 on 5 exerts an enormous force of 2431 pounds. So this is basically the critical gear that we have to worry about. So if we go to now look at the limitation, as we studied already, we have to consider bending stresses, and we have to consider contact stresses for wear. So we'll focus on gear 4, figure out the contact stress limitation, and then we verify for the bending and move on to the other gears. So if you have a gear 4, we find the geometry factor I, which has cosine and sine of the pressure angle, and it has the gear ratio 4.5 rounded. So that comes out to be 0.1315. This is the equivalent of the Lewis geometry factor for bending, but this is for contact and wear. The dynamic factor, we're going to assume Q equals 7 for the precision of the gear quality, and that gives us two parameters A and B, from which we can find the dynamic factor to be 1.18. And next is we need the face width. That's a very important parameter. So the face width is typically 3 to 5 times the circular pitch, and the circular pitch, lowercase p, is pi divided by the diametral pitch p, and that gives us about 2. So we need the width of each gear to be about 2 inches. So if we go to this website, globalspec.com, and get the pitch be 6 teeth per inch, diameter 2.67, we find that available face width is 1.5 or 2, and that is acceptable. So we're going to take 2 as an acceptable face width. That allows us, once we get F, it allows us to get the load distribution factor, knowing the 5 factors are going to there, and we can compute the contact elastic coefficient, and the other 3 parameters in the contact stress are taken to be 1, and that gives us the contact stress to be 161.7 KSI, very high contact stress. As we have learned is now that the contact stresses are usually very high, but the contact strength is also quite high. So we will have to compare that to the available contact strength of that gear. And we do that by looking at the lifetime for sigma. We want to find sigma contact allowable. For life factor Z sub n, we get the number of cycles first. So we figured it was 6 years of operation, 12,000 hours, each hour is 60 minutes, and each minute is 389 revolutions. So you get about 3 times 10 to the 8 revolutions for the lifetime of the gear. And then we can compute the cycle factor under contact to be 0.9, and all of the other 3 factors taken as 1, and that can therefore be input to compute the strength in contact to be 215.6 KSI. So that gives us an achieved factor of safety, which is sigma contact allowable, the strength times the cycle factor, 0.9, divided by the actual contact stress, and we have a decent stress intensity factor of, safety factor of 1.25. Next, we want to verify the safety factor for bending. So we would compute the geometry factor J to be 0.27, the rim factor to be 1, and then we compute the bending stress with the modified form, since we have only K sub V and K sub M and J, 3 out of the 6 parameters, with the other 3 being 1. And that gives us 38.57 KSI. Now we compute the strength, and the strength needed Y sub n for the fatigue, and that gives us an allowable strength of 58.5 KSI. And therefore, for the bendings of the gear 4, the safety factor sigma allowable divided by the actual sigma, it turns out to be exactly equal to 1.52. So as you can see here that the safety factor for contact is smaller than for bending, even though the contact has a higher effective strength. So I'm going to say, well, we have done that for the most critical gear, so it is now up to us to continue this is gear number 4, so we need to do that for gear number 2 and 3 and 5. So the other 3 gears we must check on both contact and on bending, and that is right here for you to see, and we get the final results that I'll show you here. So we can proceed the same procedure for gear 5 for bending and wear, and gear 2 for bending and wear, and then gear 2 for bending, and then we have gear 3 for bending and wear, and finally we get the final results here is that for all gears have the same pitch, 6 teeth per inch. Gear 2 is specified as grade 1 flame hardened with a strength of 170 KSI in contact and a strength of 45 KSI in tension. So this translates to a diameter of 2.67 and the face width is 1.5. And we also have determined all of the properties of the other 3 gears. So if you notice here, the gear 2 and gear 3 have a face width of 1.5, but gear 4 and gear 5 have a face width of 2, and that is important in the shaft layout. So if you look now at the shaft layout, you will see that we have this, and this is gear 2, and this is gear 3, and this is gear 4, and this is gear 5. So 4 and 5 have 2 inches width, 2 and 3 have a 1.5 inch width. Then we would choose now to support, we have roller bearings here, roller bearings for support of the input and output shaft and also the counter shafts. So we need to determine the size of the roller bearings. For the time being, we're going to take this as 1 inch on each side, and then we will do clearances for the shoulders of the shaft. So we have 3/4 here and 3/4 here, and then because we need to support in the middle section, then we're going to add 4 inches in the middle section here, and that will make the diameter of the counter shaft in the middle section to be large, as we have actually verified earlier in the same example that we studied before. So I think we are getting close to wrapping up, in which we now have to proceed. We have done a rough layout of the gearbox, and we want to proceed first with the force analysis, and that we've done earlier in one of the earlier lectures. And then we're going to do stress analysis for the shaft, all of the shoulders and the stress concentrations and so forth, which we've also done in an earlier lecture. And then we're going to do deflection analysis for the shaft, and that we've done also in an earlier lecture, and the results look like this. So the force analysis done, material selection, we selected an inexpensive 1020 cold drawn steel as a starting point, and then we did the stress analysis. If you remember, we have done this section before, section 5, design for stress, where we started from the forces, transmitted forces, and have a tangential component and a radial component on each, and then we have the dimensions of the shaft, and we translated this to a free body diagram and shear force diagram, as you remember. and the torque diagram. So this is the torque rather, and this is the free body diagram. And from those, we're able to find the load. This is the vertical shear. This is the moment, and in the XZ plane, and this is the vertical shear and moment in the XY plane. And from that, we were able to compute the critical points. If we remember here, the maximum moment, and using our design approach, we were able to satisfy all of the stress requirements and get the diameters of the shaft using the distortion energy criterion and the fatigue factors. So this has been done, and finally we have been able to size all of the shaft components on the sizes, including the shoulders, and then we have now D1 is equal to D7 equals to 1 inch, 2 and 6 is 1.4, 3 and 5 1.625, and D4 is equal to 2. These can be modified depending on the deflection, and we've done the deflection part. So this is a starting point for the deflection, and then we did deflection calculations given that we have the applied forces on the XY plane and on the XZ plane, and from the forces we obtain the moments, and the moments we integrate once we get the slope, and then we integrate another time we get the deflections of the, I'm sorry, let me just backtrack here. So from this we first have the shear force distribution on the XY plane, shear force distribution on the XZ plane. From the shear force we get the moments, from the moments we get the slopes, and from the slopes we get the deflection, as we've done in the previous lecture. So that is all finalized and finished, and then now the only consideration in this design study after we check the deflection is the bearing selection. So the bearings, this is the last part of the study. The bearings, we want to figure out if they will actually take the loads that's imposed on them. So we have to go back to the free body diagram and find the reactions at bearing A in the Z and the Y direction and the total force, and bearing B in the Z and the Y direction, the total force. And knowing that we need bearings that can last for 2.8 times 10 to the 8 revolutions, then we calculate the force, effective force on the bearing at bearing B, since it has a higher load. So B must take a very big load here, 1918. So we consider this as critical, and then we find the force as turned out to be 20,820 pounds. That's a huge amount of force that actually cannot be sustained on a ball bearing. Therefore, we have to go back and select a cylindrical roller bearing at the right end of the shaft that is a little bit bigger, and it has the ID and OD as specified. And that basically gives us the selection of the bearings as the final part of the study. The other areas that we've been familiar with is that we can decide on the keys to connect the gearing to the shaft, and the key width has to be determined by the transverse force to shear it through. So we have done that before, finding the transverse force and determining the size of each key if we choose, for example, square keys to fix all of the gears onto the shaft. And with that, we have done a comprehensive and integrated design process. I think if you have the time to go through the example very carefully and verify the formulas yourself. You will learn quite a great deal in terms of practical design of power transmission system. And beyond that, I think the next step for you to be an effective designer is to practice a little bit more as far as power transmission systems are concerned.